Welcome to our deep dive. And today we'll be tackling a topic that I think is sure to get any philosopher's mind buzzing. That's decoherence in quantum mechanics.
Oh, absolutely.
This idea really bridges the gap between that strange world of quantum possibilities
Yeah.
and the everyday reality that we all experience.
Right.
So are you ready to sort of explore how the universe goes from maybe to definitely?
Absolutely. I'm ready.
Yeah.
Decoherence really digs into some big philosophical questions, about the nature of reality itself.
Right.
At its heart, it's about how quantum systems, which can exist in these superpositions of states,
Yeah.
somehow end up appearing as the definite classical objects that we see all around us.
So are we talking about like why my coffee mug isn't both full and empty at the same time?
Exactly.
Why I don't like randomly teleport across the room?
Yeah, that sort of thing. Yeah, that sort of thing. Exactly. And it all begins with understanding how quantum systems actually interact with their environment. So think back to that classic experiment, the double slit experiment,
Right.
where a single particle, like an electron, seems to go through two slits at the same time.
Yeah, that's the one that shows how particles can act like waves and they interfere with themselves
Excellent.
and create that pattern on the screen behind the slits.
Exactly. Now, in a perfect world, that interference pattern would be crystal clear, a beautiful demonstration of quantum superposition.
Right.
But as soon as you introduce even a little bit of interaction with the environment, things change dramatically.
Oh, wow. So even like a few stray air molecules bumping into the electron
Precisely.
can mess things up.
Yeah, those interactions act like little measurements, even if no conscious observer is involved.
Wow.
Each interaction with the environment essentially forces the electron to choose a path,
Right.
and it collapses that delicate superposition.
So it's like the universe is constantly like peeking at the electron.
Yeah, that's a great way to put it.
Being like, hey, which slit did you go through? And that peaking, that interaction, causes the interference pattern to disappear.
It's as if the environment is forcing the quantum system to show its hand, so to speak, to
Okay.
reveal its position,
Okay.
which destroys the wave-like behavior and makes it act more like a particle with a definite location.
So decoherence is kind of like a cosmic editor,
Yeah.
constantly cleaning up the messy superpositions and making the universe appear more, well, neat and tidy.
That's a great way to think about it.
But if it happens so easily, why don't we see macroscopic objects like my coffee mug
Yeah,
in superposition states?
that's an excellent question, and the answer lies in the sheer number of interactions that are
Okay.
happening at the macroscopic level.
Okay.
So for a single atom, decoherence might happen due to interactions with just a few air molecules.
Right.
But for something like your coffee mug, which is made up of trillions upon trillions of atoms,
Brilliance, yeah.
the number of interactions with the environment is astronomical. It's constantly being bombarded by photons, air molecules, even tiny vibrations,
Right.
all of which contribute to incredibly rapid decoherence.
So the bigger the object, the faster it decoheres because there's just simply more opportunities
Exactly.
for those peaking interactions to take place.
That's a great way to put it.
That makes sense.
Yeah.
But I imagine there are some exceptions, right? I mean, aren't there some cases where we can see quantum effects even in macroscopic systems?
You're right, there are.
Okay.
Scientists have been able to create incredibly delicate systems
Yeah.
like squee-wides, which are superconducting quantum interference devices,
Oh,
where
right.
they can maintain these macroscopic superpositions for a very short period of time.
Right.
But the key is that these systems are incredibly well isolated from the environment.
Right.
They're shielded from all those pesky interactions that would cause decoherence.
Right.
It's like creating a little bubble of quantum weirdness within the classical world.
So it's this constant battle between the quantum world trying to maintain its strange superposition
Yes.
and the environment constantly trying to force it into a definite classical state.
That's a great way to think about it.
But this isn't just some like abstract physics concept.
Oh,
I imagine this has some pretty profound implications for philosophers,
absolutely.
especially when it comes to understanding the measurement problem.
Decoherence has sparked a lot of debate about the nature of measurement and the role of the observer in quantum mechanics.
Right.
And this is where things get really interesting for our philosopher listener.
Okay, now I'm really intrigued.
It's not just about particles and waves anymore. It's about how we make sense of reality itself.
How does decoherence play into different interpretations of quantum mechanics.
Yeah.
Does it offer any solutions to that age-old question of why we only see one outcome
Right.
when we make a measurement, even though quantum mechanics suggests multiple possibilities?
That's the million-dollar question, and the answer, as you might expect, is quite nuanced.
Okay.
It depends on your philosophical stance on the foundations of quantum mechanics. So let's start by exploring two key frameworks
Okay.
that physicists use to understand decoherence,
Right. Yeah.
environmental decoherence, and decoherent histories.
Two different frameworks. Okay, I'm all ears.
Yeah.
Let's unpack those and see how they each shed light on this whole decoherence puzzle.
Sounds good. Okay, so let's go back to the measurement problem for a minute.
Okay.
Why do we always see a single definite outcome
Right.
when we make a measurement, even though quantum mechanics suggests that a system can exist in a superposition of multiple states? This has really puzzled physicists and philosophers for almost a century.
Right. It feels like a fundamental clash between how we experience the world and how quantum mechanics describes it.
Yeah,
We just see a single definite reality, not this blurry superposition of possibilities.
exactly. And for a long time, the standard explanation involved this collapse of the wave function.
Right.
So the idea was that when a measurement is made, the system is somehow forced to choose one of its possible states, and the other possibilities vanish.
It's like magic. It's like,
Yeah, it always felt ad hoc, like patching a hole in the theory,
right, exactly.
without really addressing the underlying problem.
It's like saying, okay, we know things can be in multiple states at once, but then poof,
Right.
something magical happens when we look at them
Yeah,
and they suddenly decide to pick a state.
yeah,
That's not very satisfying.
yeah, precisely. And that's where decoherence comes in.
Okay.
It offers a much more natural and physically plausible account of how that appearance of collapse actually arises from the interactions between a quantum system and its environment.
Right.
Remember those little peaks and nudges that we were talking about?
Yeah.
Well, those interactions effectively destroy the coherence
Okay.
between different branches of the superposition, making it basically impossible to observe those wacky quantum effects at the macroscopic level.
So instead of saying that the wave function collapses when we look at it,
Yeah.
it's saying that the environment is constantly collapsing it,
Yeah.
in a sense, through those interactions.
That's the basic idea. It's not that the environment is consciously choosing an outcome,
Right.
but those interactions with the environment entangle the system with its surroundings, creating these correlations that make it really difficult to distinguish between the different branches of the superposition.
So each interaction with the environment is like adding a layer of blur to the picture.
Yeah, exactly.
And those quantum superpositions get increasingly harder to see.
Exactly. And the more complex the system is, the more particles it has, the more interactions it has.
Right.
The faster and more effective this decoherence process takes place.
Okay.
So for large objects like our coffee mug,
Yeah.
decoherence happens so rapidly that we don't even have a chance to observe those superpositions.
It's like trying to take a picture of a hummingbird's wings in flight.
Yeah,
It's so
yeah.
fast that it's just a blur.
exactly.
Okay.
So decoherence provides this more concrete physical mechanism for why we don't see quantum effects in everyday life.
It's just physics.
Exactly. But here's the catch. While decoherence explains why we don't observe superpositions at the macroscopic level,
Right.
it doesn't totally solve the measurement problem.
Okay.
It kind of just shifts the problem from the system itself to the system plus its environment.
Okay, now you've lost me.
Yeah.
How does it shift the problem?
Well, think about it this way. Before decoherence, we had a problem with a single particle being in a superposition of states.
Right.
But now, after decoherence, we have the problem of the whole environment,
Right.
including the measuring device, being entangled in that superposition.
Oh, so instead of having a single, well-defined outcome,
Yeah.
we have this massive entangled mess involving the system, the measuring device, and the entire environment.
In a way, yeah.
That seems even worse.
Yeah, it doesn't tell us why we end up experiencing a particular outcome.
Right.
It just explains why we don't see the superpositions themselves.
So it's like sweeping dust under the rug.
It's a good analogy.
It looks tidy, but it's still there.
Exactly.
Okay, so decoherence doesn't give us like a complete solution
Right.
to the measurement problem.
It doesn't.
But it does give a more physically grounded explanation
It does.
for why the world appears classical, even though it's not really.
Exactly. And that in itself is a pretty profound insight.
Okay.
It suggests that classicality isn't like a fundamental property of the universe, but more of an emergent phenomenon that arises from this complex interaction between quantum systems and their environment.
So the classical world isn't just out there waiting to be discovered.
Right.
It's like being actively created.
Yeah.
through these interactions at the quantum level.
Exactly.
That's a pretty mind-blowing idea.
It is, and it has big implications for how we understand the relationship between the quantum and classical realms.
Yeah.
But before we go down that philosophical rabbit hole, there's one more piece of the puzzle we need to talk about,
Oh, okay.
and that's the measurement problem.
Ah, yes. The elephant in the quantum room.
Yeah.
Everyone's favorite headache.
Exactly. So how does decoherence fit into this whole debate about measurement and the collapse of the wave function?
Right.
Does it offer solutions, or does it just raise more questions?
Yeah.
Well, that's where things get really interesting, and that's where the philosophical rubber meets the road.
Okay.
Let's dig into that next.
Okay, so let's continue exploring how decoherence kind of interacts with different interpretations of quantum mechanics.
Okay. Sounds good.
We were just talking about the many worlds interpretation.
Right.
What about some of the other contenders? I'm curious about Bohmian mechanics. I've heard that described as having like hidden variables guiding those quantum particles.
Yeah, Bohmian mechanics, or pilot wave theory, it's a fascinating alternative to the standard interpretation.
Right.
It says that particles actually have definite positions at all times,
Okay.
even when they're not being observed.
Right.
And these particles are guided by a wave function which acts like a pilot wave, so to speak,
Okay.
influencing their motion.
So instead of the particles being in a superposition of positions.
I always have one, but it's this hidden wave that determines where they go.
Exactly.
Mhm.
And what's really interesting is that Bohmian mechanics can actually use decoherence to explain why those particles seem to follow those nice classical trajectories that we see in experiments.
Okay, now I'm really intrigued.
Yeah.
How does that work?
Well, remember how decoherence tends to select for states that have really well-defined positions?
Yeah.
It's as if the environment is constantly measuring the particle's position.
Right.
It's collapsing those superpositions and making it appear as if the particle has a definite trajectory.
So in Bohmian mechanics, the particle always had a definite position, but it's decoherence that reveals it.
Exactly.
And that's why it looks like it's following a classical path.
Precisely. It's like the pilot wave is guiding the particle through a maze, and then decoherence is illuminating the path it's taking.
Okay.
So it makes it visible to us.
It's like decoherence is providing the evidence for the particle's position, even though it was always there.
That's a great way to put it. In the Bohmian picture.
Yeah.
But what about those spontaneous collapse theories we were talking about before?
Right.
Those seem to take a very different approach
They
to
do.
the measurement problem.
Spontaneous collapse theories, like the GRW theory, propose that the wave function itself is inherently unstable,
Okay.
and it's prone to randomly collapsing, even without any interaction with the environment.
Oh, so it's not the environment collapsing it.
Right.
It's just a matter of time before the wave function collapses on its own.
So exactly, it's like there's a timer
Wow.
for how long a superposition can last before it spontaneously decides to pick a state.
But how does decoherence fit into that?
That's a great question.
It seems kind of redundant if it's already collapsing.
That's a key challenge for spontaneous collapse theories.
Right.
Because decoherence makes systems look like they've already collapsed.
Right.
Even if they haven't truly collapsed in the spontaneous collapse sense,
Right.
it becomes really difficult to experimentally distinguish between the two.
So it's like trying to figure out if a light bulb burned out or if someone flipped the switch.
That's a great analogy.
Okay.
Decoherence is muddying the waters,
Right.
making it really hard to test those spontaneous collapse theories.
But it also highlights an interesting philosophical point.
It does.
That even if spontaneous collapse is happening,
Right.
decoherence is still shaping the world we see around us.
Exactly.
It's the mechanism for why we don't see macroscopic superpositions.
Yes.
Regardless of whether or not they're going to collapse on their own.
Exactly.
So it's still a key player, even if it's not the whole story.
It is. It sets the stage.
Like a stage manager.
Exactly.
Okay, and that brings us back to the more orthodox interpretations of quantum mechanics, like the Copenhagen interpretation.
Yeah.
Those often rely on the idea of a classical realm that exists kind of separately from the quantum world.
Exactly.
Like, there's a distinction between the observer who's in the classical world and the observed system that's subject to quantum mechanics. But doesn't decoherence challenge that separation?
Absolutely. Decoherence suggests that there isn't a sharp boundary
Okay.
between those two worlds.
Right.
Instead, there's a gradual transition, a spectrum of possibilities
Okay.
between the fully quantum and the fully classical.
So we have this continuum, this spectrum
Right.
of quantumness.
Yeah,
And it's decoherence
Yeah.
that determines where a system falls on that spectrum.
precisely.
Right.
And this has profound implications for how we understand the orthodox interpretations.
Okay.
It suggests that the classical realm might not be as fundamental as we think.
So it's not really a separate realm.
Right.
It's more like an emergent property of the quantum world shaped by decoherence.
Exactly. It's constantly being born out of the quantum world through these interactions.
This has been a really incredible journey exploring the implications of decoherence.
Yeah, me too.
It's not just some technical detail. It's a key to understanding reality.
Absolutely.
So for our listeners, we'll leave you with this thought. If the classical world is not fundamental, but an emergent pattern within the quantum realm,
Right.
what does that tell us about reality itself?
Right. Is our everyday experience just this tiny sliver of a much bigger and stranger quantum reality? And what role do we as observers play in shaping that classicality?
It's a lot to think about.
It is.
And it challenges our understanding of the universe.
Yeah.
So thank you for joining us on this deep dive into decoherence.
Yeah, it was a pleasure.
We hope you've gained a new appreciation for how the quantum world shapes our everyday reality, and that you'll continue to explore these fascinating questions about the nature of the universe and our place in it.
Thanks for listening.